Okay, let's talk about finding limits graphically. So in these types of problems, you're given some sort of a graph and you're asked to find the limit. Now first and foremost, understand that a limit can exist at a hole. So if we see a little portion here of a function f of x and we have this hole at the point 3 comma 4 and we wish to find the limit of the function as x approaches 3, well, as we approach 3 from each side, as we get closer and closer, we see that the value is 4. Okay, so here's another example to jot down. Once again, we have a graph of a function. And notice this time, we still have an open circle at 3 comma 4, but we have this point down below where it's defined at 3 comma 2. We still wish to find the limit of our function as x approaches 3. And we also are looking to find f of 3. Well, our limit is not going to change. It is still going to be 4. As we get closer and closer to 3 from each direction, the limit, or the height that we are approaching, is 4. So, again, I can't stress this enough. A limit can exist at an open circle, or a hole. However, we care about the closed circle only when we wish to determine what the function value is. So f of 3 is 2. Alright? We don't care about the hole up here. If we're looking to find f of 3, that's saying when x is 3, what is y? Well, y is 2. It has nothing to do with a limit. Let's look at another one. Okay, in this example, we have a function that has a jump in it. So it's coming along, and then we see an open circle at 2 comma 5, and then it falls down to the point 2 comma 1. It's defined here, and then it goes on and on and on. So if we are looking to first find f of 2, well, this is where we care about, is it open or is it closed? Well, to find f of 2, we care about where it's closed. So the function value when x is 2 is 1. Alright, next we're looking to find the limit of the function as x approaches 2. Now recall that that little negative up above there means from the left. So if I'm approaching 2 from the left, it means I'm actually moving to the right, getting closer and closer to 2. So from the left here, my limit would be 5. Likewise, as I'm approaching 2, but this time from the right, that's what that plus means, we're actually moving to the left. We are traveling down the portion of the function from the right. Okay, so you're moving left. So as you get closer and closer to 2, the limit there is 1. And now the overall limit, now if you don't see a little plus or minus, it means we're approaching it from each side. Well, this would not exist. So DNE does not exist because these two one-sided limits do not match up. So let's jot that summary fact down. Okay, so here it is. One-sided limits, they must equal one another in order for the two-sided limit to exist. So once again, back up here, these one-sided limits, that means as you approach it from the left and as you approach it from the right, that must be the same number for the overall limit, which we call the two-sided limit, to exist. Okay, in our last example here, we have a function broken up, and it is surrounded by this vertical asymptote. So on the left side, we see the function is going up, getting closer and closer and closer, but it's never going to hit it. And then on the right-hand side here, it's going down. So our VA is at x equals 3. So we wish to first find the limit of this function as x approaches 3 from the left. So from the left means we are coming at it over here. We're actually moving to the right. So this is going straight up as we approach 3 from the left. So here it's going to be infinity. If you were to plug in something like 2.99999 into whatever the function is, you would get a huge number. And likewise, if we want to approach 3 from the right, if we were to plug in something slightly bigger than 3, such as 3.0001, if you plug it into the function, you would see something very small and negative. So, negative infinity. Notice how These one-sided limits do not match up, so that means the overall limit as x approaches 3 from each side does not exist.